Now in this video, we're going to go through double angle identities and trigonometric equations. So let's just start with the double angle identities of sine and cosine. Now we have that sine 2 theta is equals to 2 sine theta cosine theta. So, and cosine 2 theta by definition is cosine squared minus sine squared. Now, as you can see, we have three equivalent identities for cosine 2 theta here, which are all equivalent to each other. And usually in the problem, which one to use really depends on the context and what you have given. Now, over here, if we were to just justify the last two using the original definition of cosine 2 theta. Now, over here, having cosine 2 theta to be cosine squared theta minus sine squared theta. Well, we know that cosine squared plus sine squared is equal to 1 for all theta. Therefore, if we solve for cosine squared is 1 minus sine squared. And on the other hand, sine squared theta is also 1 minus cosine squared theta. So replacing in cosine 2 theta. So if we start by replacing in cosine 2 theta, cosine squared by 1 minus sine squared, and then minus sine squared again, that would lead me to 1 minus 2 sine squared theta, which is the identity that we have here. However, if we replace in cosine 2 theta sine squared by 1 minus cosine squared, now that would lead me to cosine squared theta minus 1 plus cosine squared theta, which leads me to cosine squared theta minus 1, which is the identity we have here. So usually it really depends on the context on which one to use for cosine 2 theta. If you're working with an equation where you only need it in terms of sine, in that case you'd use this one. Well, if you're working with an equation where you'd need it in terms of cosine, in that case you'd use this identity. However, sine 2 theta is just one identity for it, and sine 2 theta would basically be 2 sine theta cosine theta. Now, in this example, we are given sine theta equals to 3 over 5, where theta is between 0 and pi over 2. And theta being between 0 and pi over 2, it means that theta lies in quadrant 1 in the unit circle. And I need to find cosine of theta, sine 2 theta, cosine 2 theta, and tan of 2 theta. So we're going to first start by finding cosine. I have sine, so which identity relates sine and cosine? That's the Pythagorean identity, which is cosine squared plus sine squared equals to 1. So cosine squared would be 1 minus sine squared. So that's 1 minus 9 over 25, which is 16 over 25. So cosine theta would basically be 4 over 5 or negative 4 over 5. So in order to know which one is accepted and which one is rejected, I'd look at the range of theta. Theta is in quadrant 1 where cosine is positive. So this one is rejected, and we'd have cosine equals to 4 over 5. Now I need to find sine 2 theta. By definition, sine 2 theta is 2 cosine theta sine theta, and I have sine and I have cosine. So I replace cosine by 4 over 5 and sine by 3 over 5, which leads to 24 over 25. That is sine 2 theta. Now, in order to find cosine 2 theta, I do have two ways I can go here. I could use the identities, the double angle identities of cosine, Or since I have sine 2 theta, I could use the Pythagorean identity in order to find sine, but in that case you'd have to determine the range of 2 theta, or the domain in fact of 2 theta. So if theta is between 0 and pi over 2, multiplying both sides of this inequality by 2, then 2 theta would be between 0 and pi. Between 0 and pi, that's covering quadrants 1 and quadrants 2. So in that case, you'd have to study the sign of cosine 2 theta, because the Pythagorean identity involves a square, and you're going to have to find the plus or minus the square root of the obtained number. So you'd have to study the sign of cosine 2 theta in order to determine which one is rejected and which one is accepted. However, by using the double angle identity, you'd avoid all of that hustle. So cosine of 2 theta, we have 3 possible identities for cosine 2 theta. We have cosine squared minus sine squared, we have 2 cosine squared minus 1, and we have 1 minus 2 sine squared. So usually it really depends on the context. If you have both cosine and sine, you could use the first one. If you only have cosine, you'd use the second. If you only have sine, you'd use the third. However, in the example we're solving, we have both cosine and sine theta, so we could use any of the 3. So over here, if we were to use cosine squared minus sine squared, that would leave me with 16 over 25 minus sine squared is 9 over 25, which is 7 out of 25. So this is cosine of 2 theta. Now we still have to find tan 2 theta. I already have sine 2 theta. I have cosine 2 theta. So tan of 2 theta would actually be sine 2 theta over cosine 2 theta. So sine 2 theta is 24 over 25, and cosine of 2 theta is 7 out of 25, so tan of 2 theta would be 24 out of 7. Now if we move to the part that tackles trigonometric equations, now whenever you have to solve trigonometric equation, the aim of the exercise would actually be to rearrange the equation or to reach an equation in the form sine x equals to sine a, cosine x equals to sine a, or tan x equals to tan a. Now these are the rules here. Now let's just discuss them a little bit on the unit circle in order to determine or to make sense out of these rules. So let's just first start by by discussing sine x equals to sine a. Sine x equals to sine a, it means that I am having 2 angles with the same sine, and we know that on the trigonometric circle, the vertical axis is the axis of sine. So having the same sine means that the 2 angles are symmetrical with respect to the y-axis. So they're either equal, that's the first case, sine x equals to sine a, they're either equal or they are symmetrical with respect to the y-axis. So if in the first quadrant we have angle A here, then in the second quadrant that would be pi minus a. So sine x equals to sine a gives me 2 possibilities, which are x equals to a or x equals to pi minus a, but we do not forget that we're dealing with oriented angles here. Dealing with oriented angles, it means that, for example, for the first case, it can not just be a, it could be a with several number of full turns. So this is why you would see an a plus 2k pi, where the 2k pi represents a certain number of full terms. It depends on the value of k, and of course here k is an integer. I could be doing the full terms in the positive sense or in the negative sense. And similarly, if it's pi minus a, if it's that angle, it could be exactly that angle or that angle plus or minus a certain number of full terms. So since k is an integer, you can see that these equations, if you're solving them in R, they would have infinite number of solutions where each value of k would give you a different solution. However, if you're working or if you're solving the equation in a smaller interval, in that case you'd have to determine according to the values of k the angles that satisfy the equation and fall in that interval. We'll see that shortly in an example. And similarly, if I were to determine the angles that have the same cosine, if you're facing an equation where you have cosine x equals to cosine a, so I have two angles that are either equal, so two angles with the same cosine are either equal, or if we look at the unit circle, they are symmetrical with respect to the horizontal axis, since the horizontal axis is the axis of cosine. So if I have a in the first quadrant, in the fourth quadrant I'd have negative a. So cosine x equals to cosine a would leave me with x equals to a or x equals to minus a. That should be an a here. So x equals to a or x equals to minus a. Of course, being oriented angles, they could be a or negative a plus or minus a certain number of full turns. So this is why we do add the plus 2k pi to the angles. Now, if we were to find the rule for tan, now if I have that tan x equals to tan a, of course, tan x equals to tan a when x is a, that's the first case. And while the second case, now in which quadrants do I have angles with equal tan? They're in fact the angles that are diametrically opposite. So if it's in quadrant 1, the other one would be in quadrant 3. If it's in quadrant 2, the other one would be in quadrant 4. So considering the first case, if I have a in quadrant 3, I have pi plus a. So tan x equals to tan a would lead to x equal to a plus 2k pi or x equals to pi plus a plus 2k pi. So over here, the angles must be diametrically opposite on the unit circle. Of course, each modulo 2 pi or adding and subtracting a certain number of full terms. However, the angles that are diametrically opposite differ by pi. The angles that are diametrically opposite differ by pi. So instead of considering both cases, each modulo 2 pi, we can just consider the first one modulo pi or plus k pi. By adding, instead of adding and subtracting full terms for each case, I just consider one case and add half a turn, add or subtract half turns. So this is why you'd actually see here that tan x equals to tan a is x equals to a plus k pi. For k equals to 0, you'd have a. For k equals to 1, you'd have pi plus a. For k equals to 2, you'd have 2 pi, so that brings you back to a. For k equals to 3, you'd have 3 pi, so 3 half turns would bring you back to pi plus a, to that point here. So in fact, this definition and that definition are in fact equivalent. You could take a and pi plus a each plus 2k pi, or you could just take a plus k pi, since we already know that tan is pi periodic anyway. So eventually, for different values of k, these two sets should give you exactly the same solutions. Okay, now if we move to this example where we need to solve some trigonometric equations. Now, if we were to first start with the first one, we'd have a 2 cosine theta minus 1 equals to 0. Now, we've seen that whenever you need to solve a trigonometric equation, you need to reach an equation in this form. Sine equals to sine, cosine equals to cosine, or tan equals to tan. So by just observing this first equation, 2 cosine theta minus 1, I'd notice that I could just solve for cosine, obtain cosine equals to half. And now what I need to do is determine which angle gives you a cosine equals to half. Now, over here, I remind you that the domains of the angles are given in radian in this example. So whenever the given is in radian, you'd have to work out the whole exercise in radian. If the given is given in degree, you'd have to work it out in degree. So over here, I have cosine of theta equals to half. So I need to find an angle whose cosine is half. Referring to the table of remarkable angles, we know that cosine of pi over 3 or 60 degrees is equals to half. Now, of course, you could use your calculators if you're on a paper where your calculator is allowed. So, however, if you're working on a paper where the calculator is not allowed, you'd actually have to know the table of remarkable angles. So cosine of theta is cosine of pi over 3. Now referring back to the rules for the equations, now we don't really have to memorize these rules. We can always just, by placing this small unit circle on a scratch, we can always figure them out. So the horizontal axis is the axis of cosine, and I have two angles with the same cosine, so they have to be symmetrical with respect to that axis. So if in quadrant 1 it's alpha, then in quadrant 4 it's negative alpha. So of course the first case where the two angles are equal, plus 2k pi, or the second case where we'd have negative alpha. So over here it's cosine theta equals to negative pi over 3 plus 2k pi. So I'm sorry, this is cosine. So this is theta equals to negative pi over 3 plus 2k pi. Cosine is half, theta is pi over 3 or negative pi over 3 plus 2k pi. So if you were to be solving in R, where theta is any real number, then these two would be your solution set, would form your solution set. So your solution set would have infinite number of angles, each corresponding to a different value of k. However, here we are given that theta is between 0 and 2 pi. So I need to find among these two sets, we need to find which ones fall in 0 to pi. So we could do that by start taking different values of k. So for k equals to 0, I have theta equals to pi over 3. Now pi over 3 is between 0 and 2 pi, so it's accepted. For k equals to 1, it's pi over 3 plus 2 pi. Now pi over 3 plus 2 pi is obviously greater than 2 pi, so that's rejected, and it will be the case for any value of k greater than 1. So we refer to the negative values of k. So for k equals to negative 1, I have theta to be pi over 3 minus 2 pi. Now that angle is negative. This is negative 5 pi over 6, which is obviously outside this interval, so that would be rejected, as well as all other negative values of k. So for the first one, the only angle that is accepted is pi over 3. Now, doing the same thing for theta equals to negative pi over 3 plus 2k pi, we need to find which angles fall in the given interval. So for k equals to 0, theta is negative pi over 3. It's negative, obviously rejected outside that interval. And obviously for all other negative values of k, they will give me negative angles, they will be rejected. So I try positive values of k. So negative pi over 3 plus 2 pi, this is 5 pi over 3, which is accepted, it's inside this interval. While for k equals to 2, you're going to be adding 2 pi to this one, so that's obviously greater than 2 pi, so that is rejected as well as any value of k greater than 2. So the solution set would actually contain, for this domain of theta, pi over 3 and 5 pi over 3. So these are the only two solutions of this equation in this domain. However, keep in mind that whenever you change the domain of the equation, the solution set could change. You could have more values that are accepted or less values that are accepted, so the solution set could change according to the domain you are considering here. Now, if I were to move to part 2, in part 2 I have -2 cosine squared of theta minus sine x plus 1 equals to 0 in the given domain. Now, the given domain, we're going to refer to it at the end when we take different values of k in order to determine the accepted values of the angle. Now, let's just aim to find that angle. Now, this is in x, this is not in theta. Okay, so we have -2 cosine squared x minus sine x plus 1 equals to 0. Now, our aim is to bring back the equation into an equation in the form cosine equals to cosine, or sine equals to sine, or tan equals to tan. And by observing this equation, you'd notice that it's impossible to do it from this equation. We'd have to rearrange this equation. We'd have to find alternative ways to reach equations in the form sine equals to sine, cosine equals to cosine. First of all, you'd notice that I have a cosine and a sine inside the equation. So the first step would be to write the equation either all in terms of sine or all in terms of cosine. Now, by looking at the terms of this equation, we'd notice that sine x, there's nothing I can do to it. However, cosine squared, since we know that cosine squared plus sine squared is 1, then cosine squared can be written in terms of sine squared. So this is what I aim for here. So using the Pythagorean identity, I replace cosine squared by 1 minus sine squared. Then I expand and rearrange the equation. So that would be 2 sine squared x minus sine x, and 1 minus 2, that is -1. So by looking at this equation, that constant I have here and that squared is still making it impossible to write it in the form sine equals to sine. However, by really looking at this equation, I noticed that I have a constant sine and sine squared. So over here I have this quantity that I have its square, and I have a term that is independent from it, which is a constant. So that reminds me of a quadratic equation. So over here, by setting y be equals to sine x, I bring this back to a quadratic equation in y, solve for y, and then once I have y, I bring back sine. So over here, we could solve this using the quadratic formula or by trial and error. Or we could notice that the sum of the coefficients are zeros. We have a plus b plus c to be 0 here. So in that case, y would be equals to 1, or y would be equals to p, the product of the roots, which is c over a, which is -half. So bringing back sine, we'd have sine x equals to 1 and sine x equals to -half. Now, I was able to reach equations in the form sine equals to sine. So first we start with this first one. Which angle has sine equals to 1? Now, of course, there are infinite number of angles that could give you sine equals to 1, all differing by full terms. However, always aim for the principal measure. So if we were to look at the trigonometric circle we have here, this is sine equals to 1, since the vertical axis is the axis of sine. So sine equals to 1, that's at pi over 2. This is the smallest positive angle with sine equals to 1. So sine x is pi over 2. Now, deducing the rule for sine the same way we did for cosine. Now, sine, we just said it's the vertical axis, so I need two angles with the same sign. So two angles with the same sign are either equal, or according to the rule, if this one is alpha, this one in quadrant 2 is pi minus alpha. So just writing the cases, it's x equals to pi over 2 plus 2k pi, or x is pi minus pi over 2 plus 2k pi. Now you'd notice that the second equation is a very particular case here, where the second equation led us to the first one. Okay, so it led us to the first one, so of course you don't keep the same equation twice, you just ignore the second one. So for the first case, I have pi over 2 plus 2k pi, which at the end I need to try different values of k to see which ones fall in that interval. However, we do have another case here where we have sine x equals to negative half. I need to find which angle gives me sine equals to negative half. However, over here, the table of remarkable angles has its trigonometric ratios that are positive. So over here, I have a negative sign. So in order to determine, using the table of trigonometric of remarkable angles, which angle gives me a sine equals to negative half, we would do it by two steps here. So first of all, I just ignore the negative. In the table of remarkable angles, which angle had a sine equals to half? It was in fact 30 degrees or pi over 6. So I just keep the negative for the moment. We're just going to do it by steps here. So first, I find which angle has a sine equals to half. Now, I have a negative sine pi over 6, and I need to write this as sine of an angle. So here we need to refer to the transformation formulas that we have taken, or basically refer to this rule where it says that if an angle in quadrant 1 is theta, in quadrant 2 it's pi minus theta, in quadrant 3 it's pi plus theta, and in quadrant 4 is negative theta. And we'd have to locate the angles based on the sign of the trigonometric ratios we have here. So here we have sine and negative. Sine is the vertical axis, it's negative here. So now what does this mean? Now over here, looking at this quadrant, it means that sine of negative theta is equals to negative sine theta, or sine of pi plus theta is negative sine theta. So if you'd remember these identities, so it's sine of negative theta that is negative sine theta, or sine of pi plus theta is negative sine theta. So I could replace negative sine of pi over 6 by either sine of pi plus pi over 6 or sine of negative pi over 6. You could choose either one. It doesn't really matter which one to choose, because eventually the second one we're going to will end up showing anyway. So over here, I'm going to go for this one. It seems easier. So sine of x is in fact sine of negative pi over 6. So again, I have over here sine x equals to sine of negative pi over 6. So according to the rule for the equations of sine, the angles are either equal, or if the first one is alpha, the second one is pi minus alpha. So x would in fact be negative pi over 6 plus 2k pi, or x is pi minus negative pi over 6, which leads to pi plus pi over 6, which is 7 pi over 6 plus 2k pi. I've mentioned earlier, it doesn't really matter which one you choose to use, because the second one will end up showing anyway. So as you can see, I did end up with negative theta and pi plus theta. So over here, if this is in fact alpha in my equation, then this is negative alpha, this is alpha, or pi minus alpha here. Okay, so I ended up with negative pi over 6, or pi minus negative pi over 6, which ended up being pi plus pi over 6, which is 7 pi over 6. So I ended up having the other case. Okay, so over here I have these three equations that represent the solutions of this equation in R. However, what I'm doing here is I'm solving it in 0, 4 pi. So what I need to do is determine which angles among these sets fall in that interval. So over here, I'm going to open in U page, rewrite the equations we have reached, or 7 pi over 6 plus 2k pi. I remind you that the angle or the domain of x we're working in is 0 and what was it? 4 pi? Let me double check. Yes, it's 0, 4 pi. So for the first one, for k equals to 0, x is pi over 2, that is accepted. For k equals to 1, x is pi over 2 plus 2 pi, that is 5 pi over 2. Remember that since we're dealing with a denominator of 2, you can estimate quickly if this is accepted or rejected, because 4 pi is in fact the equivalence of 8 pi over 2. So 8 pi over 2, 5 pi over 2 is still smaller, so that is accepted. For k equals to 2, we're going to have x equals to pi over 2 plus 4 pi. Now that is 9 pi over 2, that is greater than 8 pi over 2, that is rejected. Now over here, for k equals to negative 1, we notice that the angle is negative, that's negative 3 pi over 2. Now the domain is positive, so that is rejected. So these are the only two that are accepted for this case. Now over here, for k equals to 0, the angle is negative, so we're going to skip that one. So let's just start with k equals to 1. So it's 12 minus 1, which is 11 pi over 6. Now over 6, now let's just write 4 pi as a fraction with a denominator of 6. That would in fact be 24 pi over 6. So as long as the angle is smaller than 24 pi over 6, now that is accepted. So this is accepted for k equals to 2. Now that is a 4. 24 minus 1, that's 23 pi over 6. That is also accepted. Now for any other value of k, that will be rejected. Now similarly here, for k equals to 1, now I still have a denominator of 6. I'm still comparing the numerator with 24 pi. So for k equals to 1, that is, for k equals to 0, that is 7 pi over 6, which is smaller. It's accepted. For k equals to negative 1, it actually becomes negative. It's rejected. It's outside the domain. For k equals to 1, x would actually be, for k equal to 1, that's 2 pi. So it's 12 plus 7. That's a 19 pi over 6. That is accepted. For k equals to 2, that is 24 plus 7. That's obviously greater than 24 pi over 6, so that would be rejected. So the solution set of the equation in part 2 would actually contain pi over 2, 5 pi over 2, 11 pi over 6, 23 pi over 6, and 7 pi over 6, and 19 pi over 6. Of course, this is the solution set for x between 0 and 4 pi. If I do change this domain for x, the solution set would change. Now we still have the third equation, which is sine 2x equals to square root 2 over 2 for x between, again, 0 and 2 pi. So again, I need to write I need to write the equation in the form sine equals to sine. Now we already have the value of sine 2x here, so I need to find which angle gives me a sine equals to square root 2 over 2. Now we already have this trigonometric ratio in our table of remarkable angles, and we know that it is sine of pi over 4. Now I do have the equation in the form sine theta equals to sine beta, or sine A equals to sine B. Now again, regarding sine, they must be in quadrant 1 and 2. So if we're looking at alpha, we're looking here at pi minus alpha, because sine is the vertical axis and the angles have to be symmetrical with respect to that axis. Now, but watch out here that you are actually taking a 2x here. Okay, so it's 2x equals to pi over 4 plus 2k pi, or 2x equals to pi minus pi over 4, that's 3 pi over 4 plus 2k pi. Our aim is to find x, so we do solve for x in each case. So it's pi over 8, pi over 4 divided by 2 is pi over 8, and 2k pi divided by 2, that's a k pi. And x would be 3 pi over 8 plus k pi. Now over here, since x is multiplied by 2, when you divide the equation by 2, you divide all terms by 2, including the full terms. So a full term divided by 2 becomes half a term, etc. So we divide all the equation, including the 2k pi, by that coefficient. So over here, for the first one, for different values of k, so I have x to be pi over 8 plus k pi. I need to find the solutions in the given interval at 0 to pi. So for x equals to, for k equals to 0, x is pi over 8. That is accepted. Now for k equals to 1, it's pi over 8 plus pi, which is 9 pi over 8. Now, if we look at 2 pi as a fraction of denominator 8, that is a 16 pi over 8. So 9 pi over 8 is still smaller, so that is accepted. However, for k equals to 2, x would actually be 17 pi over 8, which is rejected, and so on for greater values of k. And for k equals to -1, for k equals to -1, that's -7 pi over 8, which is negative outside the domain, so that is rejected. Similarly, for the other one, it's 3 pi over 8 plus k pi, that's not 2 pi. So plus k pi. So for k equals to 0, we have x to be 3 pi over 8. That is accepted. Sorry. Okay, and for k equals to, sorry, let me just go back to black. So for k equals to 1, we have x to be, that's an 8 plus 3, so that's an 11 pi over 8. That also is accepted. It is smaller than 16 pi over 8. While for k equals to 2, x would be 16 plus 3, that's a 19 pi over 8, which is obviously greater than 16 pi over 8, so that is rejected. However, for k equals to -1, we have -8 plus 3, which is -5 pi over 8, that is negative, also rejected outside the interval. So the values that are accepted contained in the solution set to this equation are pi over 8, 9 pi over 8, and 3 pi over 8 with 11 pi over 8. And of course, that solution set corresponds to x between 0 and 2 pi. Again, if we do change that domain for x, the solution set would actually change.